Doing today's introduction is Dr. Patricia Pavier. Dr. Pavier is the group leader of the Radiological Materials Group at the Nuclear Sciences Division at the Pacific Northwest National Laboratory. She's also the chair of the Gen IV International Forum Education and Training Task Force. Patricia.
Thank you, Bertha, and thank you, Kobo-san, for volunteering to give this webinar. So he is the Deputy Director of the Reactor Systems Design Department in the sector of fast reactor and advanced reactor research and development of the JEA, and he has been engaged in sodium-cooled fast reactor development since 1989, when the Heisei era in Japan began. His specialty are SFR system design, safety design, and related R&Ds. Currently is involved in the development of safety design criteria for SFR as the chair of the GIF Safety Design Criteria Task Force. He has been involved with this task force since its beginning in 2011. He previously participated in the feasibility study on commercialized fast reactor cycle system and the fast reactor cycle technology development project, and he served as the design task leader and severe accident task leader in the France-Japan Astrid collaboration. One of his most impressive accomplishments is the work performed on the Eagle project, SFR severe accident experiments using IGR and out-of-pile experimental facility in Kazakhstan. He earned a Master of Science in Nuclear Engineering in 1989 from Nagoya University in Japan. So thank you so much again, Shizenobu, for volunteering to give this webinar. And without any delay, I give you the floor. Thank you again.
So thank you very much, Patricia, and thank you very much for everyone participate this webinar. My name is Shigenobu Kubo. This presentation making from Japan. Japan is now in the morning, around 10 a.m. Today's my topic is about the development of the GIF, SFR safety design criteria and safety design guidelines. Perhaps you see the page of contents. My presentation is about main part is about the development of the SDC and SDGs. As background information, I present at first some elements to be considered for the development. That include GIF safety goals and basis for safety approach, and the characteristics of sodium-cooled fast reactor, and lesson from Fukushima Daiichi nuclear power plant accidents. And part of the development of SDC and SDGs, we developed 3 documents. So I briefly introduce these 3 documents. Please go to next page. Okay, background. So concerning the safety standard of the nuclear power plant, IAEA has systematically developed an international safety standard, but it that has hierarchical structure. I'm sorry about English. The documents in the upper level standard applied for any type of reactors, so that those are technology neutral. But the lower level standards are mainly for existing railroad reactors. So our GIF project dealing with the advanced reactor. So we don't have internal standards for them. including sodium-cooled fast reactor. So there is a growing demand to set global standards for Generation 4 reactors. So our effort starting from 2011 to make a specific task force named SDC task force. This task force dealing with sodium-cooled fast reactor at first, because the sodium-cooled fast reactor here has a high technical maturity at that time. And this effort will be expand another type of reactors. So concerning the elements to be considered, at first I talking about GIF's safety goal and the basis for safety approach. Here I show the summary of the GIF's goal regarding safety and reliability. There is three such kind of goals. First one, SR1, excel in operational safety and reliability. Second, very low likelihood and degree of reactor core damage. And third, eliminate the need for off-site emergency response. In order to achieve these three goals, we set a basic safety approach as shown here. Defense in depth, combination of deterministic and risk-informed safety approach, and safety to be built in to the design, not added on, and emphasize utilization of inherent and passive safety features. Here show the explanation, definition of DID and plant states. Basically, we referred IAEA terminology and some of their definition. So, in order to concerning DID, basically we adopt their definition. So the DID levels consist of these 5 levels. First one is for the normal operation. And second, so this means the prevention of the abnormal conditions. And level 2, for the anticipated operational occurrence. This means to prevent, to expand abnormal condition to the design basis accident. And level 3, but to prevent and manage, prevent core damage and manage the consequence of design basis accident. And level 4, this is for the additional measures for the design extension conditions, which including design measures for the without significant fuel degradation and with core melting. So we think about these 5 levels for the plant reactor plant design. In addition, there is a fixed level of the DID. That is mainly for the off-site emergency response. This is basically out of the design, but some consideration in the connection with this level may be required. And next is characteristics of SFR, sodium-cooled fast reactor. Here show the schematic image to express the characteristics of sodium as coolant for the SFR. Upper part shows the advantage. This is a comparison with water. And the lower part is disadvantage. First, important point is about neutronics point of view. So in order to realize fast spectrum neutron reactor, fast reactor, we need proper materials that has lower moderation capability. So we don't need to moderate neutron. This is because the fast spectral reactor. So the sodium has a good capability regarding this point. On the other hand, water is suitable for the thermal reactor. So the thermal reactor needs a moderation of neutron. So water has a good moderation capability, but it is not suitable for the fast reactor. And next is about heat transport capability, about thermal conductivity, and so on. So sodium is used as coolant, as liquid metal. So in the reactor vessel, sodium keeps the liquid state without pressurization. So the sodium boiling temperature is around 900 degrees C. So we just keep liquid sodium inside the vessel. That is like an ordinary cooking pot. But in case of the water reactor, for the case of the pressurized water reactor, water mainly used as liquid state. So in order to keep the liquid state, PWR needs to pressurization. So this reactor vessel like a pressure cooker. So this means when we think about the leakage from the boundary, in case of sodium, leaked sodium can be maintained without backup structure, like we say guard vessel. But light water reactor case, such leakage causes loss of coolant inside the reactor vessel due to depressurization. And here show the kind of demonstration for the comparison of the heat transfer capability between water and sodium. Here is a glass tubes. One side contain water, the other side contains sodium, liquid sodium. So here is a thermography to show the heat transfer from the heat source. So this shows an example to show the good heat transportation capability of sodium. So sodium has good material for the heat removal for the core, and the coolant system can be made without pressurization. And for the disadvantages, sodium react with water and air. So we need special care about this point. Here show some a picture of the experiment of the sodium combustion in the air and water. About this sodium combustion, I'll be talking a little bit more about it in the next slide. And another point is the possibility of freezing, because the melting point is around 98 degrees C. So we need preheating of the system to prevent freezing inside the coolant system. But in the normal operation, temperature range is more than 400 degrees C. And even in the shutdown states, the temperature keep higher than 200 degrees C to prevent coolant melting. So here shows the characteristic of sodium combustion. Here shows some example, the property of the sodium as burning material. Here shows the comparison of sodium and the gasoline. This graph shows the heat generation. Gray shows the sodium, orange shows gasoline. So the produced heat is about quarter of that of the gasoline in case of sodium. And here shows the comparison of the evaporation heat. So the sodium needs more than 10 times heat than gasoline to evaporate. So the vapor pressure is lower in case of sodium. So the when we think about fire, sodium fire and gasoline fire, the flame length is very small for the sodium fire because the sodium vapor generates only around the surface of the liquid. But in case of the gasoline, the flame length is very high, so the influence of the fire has a large area. But in case of sodium, such fire influence limited to the surface of the liquid sodium. But in case of the droplet dispersion, in this case, and the interface with the sodium, the air is getting larger. So in case fire may be violent. And also we need to take care of the sodium aerosols generated as a sodium burning. So we need to take care of such a point, but by the careful design, we can manage such chemical potential of sodium. So for example, we provide nitrogen atmosphere to prevent combustion, and double wall piping to prevent leak, and early detection of the leak is one of the important points. And so again, the SFR has low pressure system. So the sodium leak may be occur, but violent leak is not likely. Here shows the summary of the comparison of light water reactor and sodium cooled fast reactor. So the LWR is a thermal neutron system and lower fissile density and lower fuel burnup. So the SFR aiming at higher core performance, including higher burning burnup and higher breathing ratio. So SFR utilize fast neutron. And the coolant system, light water reactor has high pressure system like this, and SFR has high thermal conductivity and higher boiling point. So the reactor system is keep nearly atmospheric pressure. Okay, so operation temperature of the SFR is higher. This is a good point for the power generation efficiency. But we take care about the influence of such higher temperature in the reactor materials. Here shows the comparison of the reactor cooling system between light water reactor and SFR. Left-hand side is an image of the PWR. So here is a reactor core and reactor coolant boundary and reactor containment boundary. And in case of PWR, there is a steam generator connected to the turbine. And for the water leakage, so-called loss of coolant accident, in order to cope with this, there's this kind of various systems to water injection. And in case of SFR, core is here, and reactor coolant boundary is like this, and reactor containment boundary like this. And as a conventional system, SFR uses a steam generator for the power conversion. So in order to prevent the influence to the core, we introduce a closed secondary system. So this system has intermediate heat exchanger between the primary system and secondary system. Primary system and secondary system is sodium coolant system. And for the heat removal, in case of SFR, leaked sodium can keep this dotted line system. This indicate a guard vessel or guard pipe to keep the leaked sodium with this vessel-like structure. And for the heat removal, here is so-called decay heat removal system. So this decay heat removal can be achieved by the heat transfer from the core to this heat exchanger, and there is a secondary sodium circuit, and heat transfer through this secondary system to the atmospheric air. So here is the air exchanger here. So in case of primary coolant leakage, in the normal operation, primary coolant, of course, keep inside the reactor coolant boundary. This is both of PWR and SFR. But in case of the primary coolant leak, the leaked coolant dispersed inside the containment vessel in case of PWR. But such leaked sodium can be maintained backup structure like guard vessel and guard pipe. So the core can keep inside the liquid sodium. So core keep covering of the liquid sodium. This is the important point. Here again, schematic view. This is just for the SFR system. As I explained, there is a decay heat removal system like this, and core and reactor boundary and containment boundary like this. And for their chemical reaction here, maybe steam generator tube failure might happen. In such case, water vapor injected inside the secondary sodium circuit. So in order to mitigate such situation, we provide the countermeasure like detection and blow pressure release, reaction products treatment, something, etc. In order to mitigate sodium water reaction, we make such special care. Thanks to these design measures, we can prevent influence on the core of such accident. So here's a summary of the characteristics, safety characteristics of the sodium-cooled fast reactor. Here shows some safety advantages. Low pressure coolant system. So they are, in order to keep the core submerged under liquid sodium, we provide guard base and guard pipes. And we don't need a high pressure injection system, because no risk of the loss of coolant accident due to their depressurization. So the core has inherent safety features with net negative reactivity feedback. And there is a large margin to coolant boiling. And as I explained, we provide a dedicated system for the decay heat removal to ultimate heat sink. So this is this can be made by utilizing liquid metal coolant, good point, excellent thermal conductivity, and natural circulation characteristics. So this system can be operated without electric power. This can be operated passive manner with natural circulation. So the containment system itself doesn't necessary to keep the higher pressure tolerance. But we need to care about sodium fire. And another point is about sodium retention, retention capability of the fission materials in case of the core damage situation. Sodium has good capability for the retention of the non-volatile or some volatile fission products. And we don't need to care about depressurization. The operation itself is not so complicated, so we can make a simple operation, and we can keep the long grace period by utilizing the sufficient margin to coolant boiling. Here shows the challenge for the SFR. So this system has high temperature and high core power density. So we need to care about this point. So we have developed a good material to cope with the creep damage in such higher temperature and higher power density, and also the higher neutron fluence. And concerning about chemical reaction, we need the adequate prevention and mitigation measures for the such effect of the chemical reactions. And in the core, this is the fast neutron system. So the core is not in its most reactive configuration in the normal operation state. So if we think about core voiding, positive void effect may arise, but we can take carefully about such situation, and even in the design extension condition to mitigate core damage. And sodium is liquid metal, so the sodium has no transparency. So we have a special development for the inspection and maintenance. And the lesson from the Fukushima Daiichi nuclear power plant accident. So this tragic accident happened about 9 years ago here in Japan. That was severe earthquake and tsunami hit it around the northwest side of Japan. And Fukushima Daiichi nuclear power plant got severe damage. So we never get such severe accident again. So we take care to cope with severe external event which may cause a long-term station blackout and loss of cooling function. So for that purpose, we have design measure for such severe external event cases. Also, enhance the design measures against such kind of severe accident. And okay, so in case of the Fukushima accident, the loss of heat sink happened as a result of tsunami. This is because ultimate heat sink of the plant, major ultimate heat sink is seawater. But most part of the such auxiliary system lost its function due to the tsunami. In case of the sodium cooled reactor, as I explained, decay heat removal can be made through the decay heat removal system. The system is mainly used atmospheric air, not the seawater, as the ultimate heat sink. So this is a good point for the SFR. So we need to utilize such capability of SFR to cope with such kind of severe plant conditions. Okay, so next is about the outline of the SDC and SDG for Generation 4 sodium cooled fast reactor. So our SDC task force developed 3 kind of document, SDC and SDGs. This is aiming at providing the common design safety approach and possible application to the design. So the member of SDC task force come from China, EU, France, Japan, Korea, Russia, United States, and we have an observer from IAEA. These countries have their own project for the SFR development. So they have their own experience and design concept and R&Ds. So we gathering such information in this task force and try to make common understanding of the safety aspect of for the SFR. We already completed these three kind of documents, and now we SDC task force is reflecting feedback in the document from external authorities such as national regulatory bodies of the countries, IAEA and OECD NEA, WGSA. WGSA is a working group for the safety of the advanced reactor. And our task force participates in the GIF IAEA joint liquid metal fast reactor workshop on safety. And we will develop SDC for the other reactor systems through activities of the RSWG, Risk Safety Working Group of GIF. So here's the hierarchy of the safety in our GIF. So SDC is located here, and SDG is located here. Here shows the SFR design options in GIF. We have several design concepts. One is a large size loop type design. This has been developed in Japan. And intermediate to large size pool type reactor. This has both of oxide, loop type has oxide fuel, and pool type has oxide fuel and metallic fuel. Pool type has another concept of small size modular type design like this. Here shows the process or relation between the SDC, SDGs. SDC is here. This corresponding to the IAEA SSR 2/1. This IAEA document is for the design of mainly for the existing light water reactors. So we referred this document, and we made a generation SFR version of such kind of criteria. So this criteria including about 80 criteria, about 200 paragraphs, 200 statements. This including safety approach and SFR characteristics and lesson learned from Fukushima Daiichi accident. And in the for the application guide, we provide two kinds of the safety guides. First one is for the SDG on safety approach and design conditions. This including both of general part and some of specific part. General part including about the definition of plant conditions such as AOO, anticipated operational occurrences, and DBA, design basis accident, and design extension conditions, DEC, and also for the practical elimination of accident situations. As for the specific point, we cover reactivity issue and decay heat issue with this document. In the next SDG document, this SDG document is for the key structure systems and component of SFR. This document covers the reactor core and reactor coolant system and containment system. In order to develop these three kind of documents, we gathering the information from the member from the task force about design options and design conditions. This means an actual design and related development activity of this from the member countries of the task force. And also we refer some of the IAEA document. Here is IAEA SSR 2/1. This is a generic design requirement. And also IAEA NSG series, this document covers design guidelines for the specific system of the nuclear power plant, including reactor core, reactor coolant system, and containment system. But this covered for the existing right for the reactor. Okay, so I showed the outline of three SDC, SDG document. First one is SDC. So this document is available on the website, GIF website here. So if you are interested in this, you can see the document at this site. Here show the table of contents. As I said, the first part covers the generic safety approach that can be applicable for the most of sodium cooled fast reactor. Sorry, this is SDC. So this document covers the important element, as I explained in the first part of this presentation here, sorry. And from chapter 3, this document describes the each of the criteria, which including the 80 criteria and about 200 statements. Criteria number 1 to number 42, rather generic part. And in chapter 6 covered design of specific plant systems, including the specific plant system of the SFR. Reactor core system, the reactor coolant system, containment system, and so on. Okay, so the next is a guideline. Here show the first SDG document, SDG on safety approach. This document is also available on the website. So this document to provide recommendation or guidance, how to comply with the SDG. So here is the contents of the document. So the chapter 3 covered the general approach. And chapter 4, rather specific one for the SFR. Reactivity issue and decay heat issue. And okay. Chapter 5, yeah, there's a specific chapter to deal with SFR characteristics of the reactivity control. Okay, here show the some of the general design approach from the SDG on the safety approach. Basically, the safety concept and safety design is to use the multiple redundant engineered safety features to lower the probability of the accident and to limit the consequence for the AOO and DBA. So these features include independent or diverse system engineering safety features. In addition to these, passive and infinite features for cooling and shutdown and power reduction also play a significant role to cope with the design extension condition that has a diversity to the active engineering safety features. So the here show the part of the engineering feature can cover, and for the design approach or design extension conditions, we provide some additional measure. For this, our concept is to introduce a passive and inherent feature to prevent core damage and to mitigate core damage. These two design measures corresponding to the level 4 of DID, and they are with design extension conditions. Here shows some example of the typical AOO and the DBAs for SFRs. So such events may be results of imbalance of core power and cooling. So there's some mechanisms about such imbalances that include core power increase, primary current flow decrease, and abnormality in heat sink. So here shows typical events that causes such mechanisms and challenges. And for the design extension conditions, for the prevention of core damage, passive and inherent safety feature will be introduced to control reactivity and to remove decay heat decay heat. So inherent reactivity feedback and passive mechanisms will be used to control the reactivity even in the anticipated transient without scrum. And for the decay heat removal, natural circulation capability should be introduced, and various configuration. I'll explain later on. We called various configurations such as DLUX, PLUX, and RLUX. For the mitigation of core damage, our strategy is investor retention. So even in the core damage situation, damaged core material should be kept inside the reactor vessel. For that purpose, we think about mitigation of the to release mechanical energy due to the recriticality, and keep the degraded core material as a coolable inside the reactor core. For that purpose, we provided the core catcher inside the reactor vessel. And also, we provide permanent heat removal path. For this purpose, core should be submerged under liquid sodium, even in such core damage situation. Here show about practical elimination. This concept is a little bit complicated. Here show the IAEA's terminology, the practical elimination. This term was used in requirements for the design of nuclear power plants to convey the notion that the possibility of the potential occurrence of certain hypothetical event sequence in serious scenarios could be considered to be excluded. To say such situation to be excluded, we need to demonstrate such situation is physically impossible by design or with residual risk with high degree of confidence. Situations which may lead to early or large radioactive release and which cannot be mitigated under acceptable condition. This means when we provide design measures for the mitigation, that needs a very expensive design measure that cannot be acceptable. So in such case, should be identified and practically eliminated by implementation of design provisions. So we need to provide design provision to say such situation is practically eliminated. That is important. So the practical elimination can be considered as a part of a general approach and as an enhancement of the DID principle. But such situation should be very limited list of situations. Here shows some example of such situations. One example is power excursions due to the large gas bubble passage, large scale core compaction, something like that. Situation leading to the failure of the containment risk. We should practically eliminate complete loss of decay to level and core uncovering situation and core damage during maintenance and spent fuel melting in the stretch. Finally, I'm talking about SDG on the structure system, the component. Here shows the table of contents. This guidelines covers the reactor core and the coolant system and the containment system. Unfortunately, this document is not available in the website, but this may be available in the near future. This document has a variety of the appendix and annexes to help the reader to understand the contents of these guidelines. This including about example of design concept of active reactor shutdown system and passive reactor mechanism and so on. So this document mainly covered design features of SFR, which summarizes 14 points. These 14 points included in this document. This orange part is for the reactor core system that covers core and fuel integrity and reactivity control. And for the containment system, also integrity of the component and the primary system, and measures against chemical reactions and decay heat removal, and the containment system. We discussed about SFR specific load conditions for the containment design. So talking about some of the example of the design for the decay heat removal system. As I say, we can choose. This selection can be made by the designer. We can make various configurations of the decay heat removal system, as shown in this figure. So the Deluxe has heat exchanger inside the reactor vessel. Plux has the primary circuit, and Ilux has the secondary circuit. And Rbox cooling can be made outside the reactor vessel, like this. Here show the example for the design for the decay heat removal system. This is the example for the JSFR. JSFR is loop type design. So this design has Deluxe like this, and Plux. Plux has a heat exchanger inside this primary pump and intermediate exchanger vessel. In addition to this system, there is an alternative cooling system. This system is independent from the main cooling system. Here show the example of the athlete design. So this athlete is pool type design. So two diversified inverse cell decay heat removal system is here. One in the passive decay heat removal system, and the second is active decay heat removal system. And these two systems is has diversity in the configuration. And in addition to this, heat removal from the outside of the safety vessel is introduced like this. This is the example of the PG-SFR by Korea. So here is two diversified decay heat removal system inside the reactor vessel like this, and also cooling system from outside the safety vessel. Here show the cooling path, cooling inlet, air inlet and outlet to the reactor cooling, vessel cooling. Okay, that's all my presentation. Here, the concluding remarks. As a part of development of GIF reactor systems, GIF is developing SDC and SDGs. Based on the consideration about the basic safety goal and basic approaches of Generation 4, and the safety characteristics of SFR, and lesson learned from Fukushima Daiichi nuclear power plant accident. And also we gathering the information from the various design of the member countries to develop this SDC and SDGs. And as a result, we have developed three kinds of document, SDC and two SDGs. And GIF is making effort in reflecting feedback in the documents from external bodies and participating in the activities such as GIF IE joint workshop. And this effort now going to develop as a type of reactors. So that's all. Thank you.
Thank you, Kobo-san. If you have questions, go ahead and type those into the Q&A pod. And while those questions are coming in, we're going to just take a quick look at the upcoming webinar presentations scheduled in March. Microreactors, a technology option for accelerated innovation. In April, the GIF VHTR Hydrogen Production Project Management Board. And in May, the performance assessments for fuels and materials for advanced nuclear reactors. There are a few questions. The first of which reads, how are AOOs and BBAs in the design extension scenarios determined?
May I answer by oral?
You bet, absolutely.
Yeah, sorry, I cannot write down so quickly. Concerning the AOO ZBAs, one aspect is occurrence probability. So the lower bound of AOOs is about 10 to minus second per reactor year. For the DBAs is about 10 to minus 4 per reactor year, something like that. But our consensus is just only for the AOOs. So the such lower limit value is indicated in the SDC or SDG document. And another point is coming from the experience of each countries. Each country has the experience of the development of SFR, and some country has the experience of the licensing application. And such experience can be the basis to select AOs, DBAs. And in the past, we don't have any design extension conditions, but we have some experience to evaluate beyond the design basis accident. So such accident can be a basis to select the design extension conditions.
Thank you. The next question is, what keeps the core melt stay in the core? Maybe I read that incorrectly. What keeps core melt? Yeah.
Yes. We think about the kind of the core damage due to the failure of the reactor shutdown. In this case, core damage may happen due to overheating. So in such case, core melt situation may appear even with liquid sodium remain inside the reactor vessel. So we can keep the damaged core inside the reactor vessel. But we take care about leak criticality. When we think about molten core materials remain inside the reactor core region. So we think about molten fuel discharge from the core area outside the core area, but such molten fuel still keep inside the reactor vessel and still keep on the liquid sodium. And in order to make sure to hold such degraded core material inside the reactor vessel, someone will design installed in-vessel core catcher in the bottom of the reactor vessel.
Great question. The next question is, are there any SFRs under construction?
Next question. Yes, we in the world we already have a lot of experience of the construction of SFR. The oldest one is in the United States in 1950. That was the experimental reactor EVR1. From that time, in the world, we developed SFR technology. From the starting point, we developed experimental reactors. That smaller one, but liquid-cooled fast reactor. Such experimental reactor were built worldwide now, and now China constructed such experimental SFR. And also the prototype reactors and even the demonstration type reactors constructed and operated. Especially in Russia, now they are operating BN600 and BN800. Those reactors in their stage of the commercial operation.
Excellent, thank you. The next question asks, has GIF considered making the SDC and SDG documents available to designers or vendors?
Yes, sure. First objective of our development is to provide such a document for mainly the designers and the vendors. So we try to collect a good practice from the member states to provide such information to the designers, vendors. But we need communication with the regulators. So we get feedbacks from the regulators. So such activities are important. So now we have connection with IAEA and OECD near WGSR.
Excellent, thank you. That's all the questions I see in the question pane. Are there other questions that anybody has as an afterthought? We can hold on for just a minute if people have questions, want to type those in. While we're waiting, I do want to take this opportunity again to thank you, Kubo-san, for your efforts and your putting this presentation together and sharing your expertise with us this evening or this morning, depending on where you're at internationally. It's been a pleasure working with you, and I appreciate your effort very much.
Thank you very much for the time.
Yeah, thank you again, Kubo-san. It was very good.
So is it okay to go back my work?
Yeah, I don't see any more questions coming in, so I think we'll go ahead and close the presentation for today. Thanks again. Have a great day.
Thank you very much, everyone.